Hello everyone. Today I'm going to present about correlation, regression and machine learning for all the professors, researchers, graduates and postgraduates out there who are curious about it. So before that, I'll just share a quick incident with you that happened today. So there was this Mr. Copilot and Miss Gemini, and they were arguing indirectly about my presentation, that what should be added and what should not be added to my presentation. And ChatGPT on my right hand side was like, why don't you add some exponentials? Why don't you add some extra variables? And etc. etc. And I was like, why don't you present instead of me? And the obvious response was, we do not have that feature right now. Well, for that, maybe it'll take few months or years, I don't know, but that was the thing that I wanted to share. But all the smart readers out there, you must have read about correlation, and we'll just do a quick introduction about it. What is correlation? Correlation is when two variables are related, say x and y. What is causation? When we know about the cause and effect relationship of those two variables. For example, I have on y-axis I have got rainfall. On x-axis I have got crop yield, and I know because of increase in rainfall the crop yield would be increased. This is how we used to study, right? Oh, here correlation does not, it's not bot, it's not my typing error. Correlation does not only establish the relation but also quantifies it. Cause and effect relation is not determined by correlation. So let's move to next slide. What are the types of correlation? We all know that. Just a quick recap. Positive correlation, when the variables are related in the same direction, then this is known as my positive correlation. In economics also the supply curve. And my negative correlation, when variables move in the opposite direction. So then we have got our negative correlation when the change is in opposite direction, and this is also our demand curve. So that's about the positive and the negative correlation. Some of the examples of the positive correlation are height and weight, price and supply, amount of rainfall and yield of crop. And some of the examples of the negative correlation are volume and pressure of perfect gas, price and demand of goods. Let's move on. So positive correlation is also called as direct correlation. Increase in x causes increase in y. What would be negative correlation? The negative correlation would be downward sloping, and it would be increase or decrease in the value of one variable would decrease or increase the value of other variable. So let's move on to the types of correlation. When I say about simple correlation, then we study only two variables, x and y, or x1, x2. When we have got partial correlation, then we study, suppose we have got 10 variables and we only study 5 variables in first test, and then 5 variables in other test. There can be various permutations and combination. And when we talk about multiple correlation, then okay, again a typo, 2 or 3 variables depend linear correlation forms a 45 degrees line. Now moving on to the nonlinear linear and non-linear correlation. So what do we see over here is that we have a y is equals to 3x plus 1, which is equals to y is equals to ax plus b, and where a is the coefficient. So the constant value that is changing is 1, and the 3x over here is the coefficient of our value x, and our x is over here the dependent variable and y is the independent variable. So far so good, we have studied everything. Then what is the nonlinear variable? When the relationship is uh, not linear, but kind of a non-linear relationship, which can be more of a quadratic form. So it would be y is equals to a plus bx plus cx cos raised to the power 2. So this can be polynomial, any polynomial, or more generally a polynomial, which are normally plotted like this. Okay, so now next is, so when we have a strong non-linear relationship, then we get a U-curved. Now we have different measures of correlation. Scatter plot, we have when we visually plot it, we can have a general idea of correlation. It can be high negative, high positive, low negative, low positive, or zero correlation. So graph method is similar to our scatter plot. And then correlation coefficient is something that measure the strength of linear relationship, and it is by r, so denoted by r, so we can say rxy or ryx. And then we have, this is our summation sign, x minus x bar. This is our mean, y minus y bar. So variable minus the mean, this is our mean deviation, arithmetic mean and deviation. This is arithmetic mean, this is the deviation. And then here we have under root of summation x minus x bar over y minus y bar. This y minus y bar, this is our Karl Pearson coefficient of correlation, and we can have its values from 0 to 1. X over here is our independent variable, y is our dependent variable, and y is our dependent variable. And what else do we have over here is just that when r is greater than 0, it denotes positive correlation. When r is less than 0, it denotes negative correlation, and 0 is that it does not have any correlation. Basically, correlation was given by Sir Francis Galton. Okay, moving on to the coefficient of correlation. So that was the Karl Pearson's coefficient of correlation. When we have a frequency data, then we just add the n over here in our formula. For n is the frequency, denoted by frequency. And then we have studied a lot of times how do we open a plus b whole square, how do we these are the derivations that we have learned in +2 and graduation, so we all know how the background of these works. Now this is a scatter plot diagram. This is our positive correlation, this is our supply. Basically, this is a negative correlation, this is our demand, this is our low positive correlation, this is our no correlation, zero correlation, this is also zero correlation, and this is also zero correlation. We will understand how does this helps us if we have to regress it, then how we can obtain the values, because in correlation we cannot do it, but in regression we can plot it. We have already studied in our basic mathematics in 12th and in graduation that this is our like ellipse, parabola, hyperbola. This is our hyperbolic function. When we have different domain and range, for our range we use the range variable, and then domain can be negative and positive. So if it was a little bit of like down here, it could be have gone to -2, or the domain could have gone to -3. So this is the equation that we have in our background from our calculus and integration and linear algebra. So all that we have already studied. Now the correlation coefficient, we already know one is strong and -1 is strong negative. This is the range of correlation coefficient. Now let's move on to the regression, which is the main part over here. So when we study regression, what is regression basically studied? Regression is basically studied to predict the value of the variable. The prediction part that happens is when we regress any number of variables to find out that what would be our uh, prediction of the coefficients, that is the alpha, beta, or the estimation. So this is something that we use to understand or predict about a variable or a set of variables. So that's pretty much the basics that we study in graduation, and sometimes we also study this in post graduation for MBA student, BBA students. So we know what is regression. It is like there are different types of regression: simple regression, multiple regression, and how do we estimate in regression. So yeah, I hope everyone is familiar with it, and if not, they can just comment, and maybe I can tell you about what kind of variables and variances and errors we have, and why do we assume our error term to be like 0. So that's it. Now we have the types of regression models. Like we have the positive regression. Here, do we have a regression? Yes. What kind of relationship is here? Non-linear. Here it is negative and no relationship. Now see, there is a difference between population and the sample. So population is the whole population, that is a geographical location or whatever is the population that you are considering, and sample is a part of the population. So whenever we use normally the population in linear regression, it is denoted by capitals beta. So here y is dependent variable, this is our y-intercept, this is our coefficient, and it also tells us about the slope. This is our independent variable. So this is the predicting variable, and this is the variable that has to be predicted, and this is epsilon, that is random variable, which we have to minimize. That is why we in the background we have studied sum of square errors that has to be minimized. So how do we minimize it? By taking the deviation from mean deviation and then squaring and underrooting it so that the value of the error term is minimized. That is what all we have studied, and then we started studying the patterns in the error term as well, and white noise, that is something that is in the econometrics. Now the population linear regression. When we talk about the population linear regression, so this beta 1 is the slope, that is the change. This can also be the tangent. This is the observed value, and this is our predicted value. So whatever is this distance between the observed value and the predicted value, that is the random variable for our x value, which is our independent variable, and y is the dependent variable, and this is the intercept or the constant that we have, which can be any constant, and we know the derivative of constant is 0. So all that will be used later. Now next we have the estimated regression model. So that is the sample regression. So the sample regression provides an estimate for the population. We use the parameters. So parameters are used for the population, and when we have to estimate it, then we use the estimations, and they are normally denoted by a cap over their head. So yi cap, this is the estimated or the predicted value. Small beta naught or the small letter is used for the regression intercept of the estimate. Estimate of the regression slope is beta 1, and x over here is the independent variable. So the individual of random error E1 have a mean of 0. So we have this like our. So in regression analysis and machine learning, we'll cover three topics today: linear regression, gradient descendant, and regression equation. So how do we go about when we have machines that we provide an input to the machine? The machine provides us an output. The input function is for the algorithm and the output function is for the user. Similarly, if you want to have an hypothesis, then we can, in the hypothesis also, we provide input values, that is the value of the dependent variable, and then we get an output hypothesis, an output which is the value that we are trying to predict, right? So now how would we go about in the supervised learning regression? So we have suppose you have given x and you have to find y. Let's say that you want to predict the price of the houses. So you have a variable size, that is the x variable, and what you have to predict, you have to predict the prices, that is the y variable. Now how would this hypothesis be generated in normal regression? It would be y is equals to a plus bx, and then we would probably go about the sum of square methods and the sum of residuals and find out a best line fit with the ordinary least square. But if we have to do it with the machines or the, then how would that hypothesis be created? Now that hypothesis would be, suppose it's for x, it would be hx, hypothesis for x, where we have a q0 plus q1x. And what is this known as? This is known as affinite function. Now we have to add more variables to it. We have only got one variable. Suppose you have to add another variable to it. And what is that variable? The bedroom, the number of bedrooms. So now you have two variables. One is x, that is the size of the x1, that is the size of the plot or the house only, and x2, that is number of bedrooms. And you can add more variables to it, which can be number of bathrooms, parks, parking area, number of car parkings, and as many variables as you want to predict the y variable, which is price. Let's keep it simple for now. So initially, how did we represent the hypothesis hx? We said that the hypothesis would be q0 plus q1x, and this is known as our affinite function. Now we have x1 variable, which would be size, and we have our x2 variable, which would be number of bedrooms. So now how would our hypothesis be? hx is equals to q0 plus q1 x1 plus q2 x2. These are our dependent variables, okay, and what we have to estimate would be our independent variable. So number of bedrooms can be 2, 3, 4, so on. So now what would be our hypothesis? You know, hx is q0 plus q1
x1 plus q2 x2. So for n numbers, we can have it till n numbers. So when we have to add two variables, suppose I have to add x1 plus x2, how do I write it? Summation I is equals to 1 to x. This is what we have learned. Now what would be our hx? It would be summation, let's take the variable j is equals to 0 to 2 qj xj. Now for conciseness, we can say that where x0 is equals to 1, this would be our dummy feature. So far it's going like, okay, this is all we have understood. Now the question is, when we have q over here, how would our q be represented in a vector form, in a qx? Before qx there is q, so this can have a form of q0, q1, q2. Because how many we have the x factors? The x factors are there, 2 factors, and we can have the x also. If we want to increase our x factors, we can have x0, x1, x2, and so on. Now what is our theta or q? Now theta, we have this theta. We know how did we represented our hypothesis. We had our hypothesis as hx is equals to summation j is equals to 0 to 2 qj xj, and we say where x0 is equals to 1, and we added a dummy feature. So a theta, the parameter, theta parameter here would be q0, q1, q2. Now this is for the various options that we have. And then our x would be, say we have different x's over here, x0, x1 number of bedrooms, size of plot, size of house, so on up to xn. And then what is theta over here? This is our parameter. And what does this parameter allows us to do is to make good prediction about the houses. So the difference between parameter and estimate is that parameter that is used for the population, estimate is used for the sample, and then we have a concept of estimation of errors as well. Now for this training example, we have that allows you to make good prediction about prices of houses. We have m, suppose we have got m, which is the number of training examples. This is my number and this is my examples. So this number m, the training examples, would be rows, and these rows would be each house. Houses are the rows. And over only I would like to tell you that x is our input feature, and y is our output that is our target variable, that is our output function. Okay, so far we have understood how do we formulate the hypothesis, and hypothesis and notations are something that can be used interchangeable, but for some reason hypothesis became popular. So far we have learned that x is our input variable, right? X is equals to our input variable and y is equals to our output variable. So x is the size and y is the price, and the output variable is also known as the target variable. For the notation purposes, we have x comma y, which is equals to training examples. So now we are writing an index into the table of examples, which would be x I comma y I, which is our ith training examples. So from the table itself, now we'll study x1i. What would be our x1i? It would be 2104. 2104 is first house in the training example. Now what would be our the second, the x2 variable? It would be 1416. Okay, this is how we used to study about our regression models as well, right? So n over here is number of features. How many number of features do we have? 2. So our hx was, what was our hx? Summation I is equals to 0 to 2 qj xj, and x and theta, this is 1 plus n. And what does this tells about dimensions? We remember about the degrees of freedom. How was it? N minus 1. So similar notation, it's like x and theta is 1 plus n, like doing again and again, we have understood it. Now see theta will be having our, how many values can theta also take? Like it can take how many values? 0, 1, 2, so on up to n. And how many values can x take? x0, x1, x2, so on up to xn. Now so far clear, x and theta would be 1 plus n, which would give us the data set. Now given a data set, given a definition of hypothesis, how do you choose parameter data? So we choose theta such that hx is approximately equal to y for the training example. So we'll write here, we'll choose theta such that hx is similar to y for training example. So where training example is x and y. What was our h theta x? The hypothesis. And this hypothesis depends upon both on theta and input features. What were our input features? x1, x2. So for notational convenience, what we say that h theta x is equals to hx. We'll have to remember this. If you have notepads, write it down somewhere. Now, what are the correct asking prices for those houses? We have to, for that, we have to minimize. So how do we minimize it? H theta x minus y square. The minimization thing we learned earlier as well. So we'll say we have to minimize it. We'll write minimize 1 by 2 summation. We'll add 1 by 2 over here. 1 to m, number of training examples. H theta x ith index minus yi whole square. You remember sum of square of residuals and SSE sum of squares of error terms. 1 by 2 is summation I is equals to 1 to m. It would be h theta x I x to the index of I, y to the index of I whole square. What was our cost function? What was our cost function? J theta. So this J theta is equals to 1 by 2 h theta x I index minus y I index whole square. Now the cost function has to be minimized. Okay, so now we have our cost function. What is our cost function? J theta, which is equals to 1 by 2 h theta. What was our x? X to the I index minus y to the I index whole square. So we have to always minimize the cost function, the error term. So we have, what are we doing here? Now we will do the generalization of linear model using square error corresponds to the Gaussian function that we studied. So we also study the ordinary least square method. So we have to now use what? Square error. And how does we get that? By the methodology of Gaussian function. And why do we use the square error and not the R4 or any other error? We'll study in next class, next week, next Sunday. So we had, what was our X? The square feet. Rooms. Number of rooms. And then we had prices, which have to be predicted. Okay, before telling you about the R4, we have to learn about the gradient descendant as well. And next class, we'll cover the gradient descendant. For now, we know that we have understood the cost function, which is our J theta. And we have to minimize the cost function. How do we represent the j theta? We have discussed it. Now, for this theta value, we have to find some value. And for the some value of theta, we can say that theta is equals to 0 vectors. This is from the calculus. Now we have to keep changing the theta. Why do we keep changing theta? To reduce the j theta. And to minimize the j theta, we have to use our gradient descendant. But before that, we have the values of theta 0, theta 1, which are our random values. It's just like a guy who is standing on a hill and he turns around, like, okay, he's like turning around, and this guy wants to go downhill as quick as possible. So he have to find the most steeper, or we can say the steepest pathway. So you have to get a pathway, and your pathway would keep on changing. Which one would be your local optimal? When the training set is fixed, cost function is fixed. So we'll start with some value of theta, that is 0 vector, which keeps on changing so that the theta function is minimized, and we have to solve j theta. Okay, for today it's till here. Next Sunday we'll catch up with the gradient descendant and to find how can we minimize this. Okay, bye bye.